Hello, everybody. Thank you very much for joining us today at our first meeting of the PACE Land Data Users Group. We have a pretty great agenda ahead. We're going to start with a top-level overview of PACE, its land products, as well as the objectives of this group and how to join. Then next up, after that, we're going to see some of the first science insights being gleaned from this PACE land data by Fred Huemmrich. And then as our third presentation, we're going to have a short informative overview of where you can get the land data. As for a couple of logistics today, the content is written under the assumption that all of you here are pretty familiar with downloading and interpreting satellite data products. I'm going to note that our information is current as of April 2025. Keep an eye because data versions, access points, resources evolve. Also, everything that you see today will be available on an event archive located at that website right there. We will have a recording and we'll have slides as well as a transcript of the question and answer sessions. So let's go ahead and dive in. My name is Morgaine McKibben. I lead the applications program for the PACE mission. And today I'm going to go over the PACE mission and tell you which land products are available. I'm also going to tell you some best practices for using the provisional land data and let you know how to join our group and what our objectives are. So let's start big with a really broad, zoomed out version. This image is showing NASA's current Earth observation fleet. From extended missions that have been collecting data for decades, like MODIS, Aqua, and Terra, who's now about 25 years old, spiraling out in time to the newest missions, such as PACE, launched just last year. We also have here a look ahead at future projects currently in various states of on-the-ground development. So PACE was designed to bring a novel set of advanced ocean and atmospheric observation capabilities to NASA's world-class Earth observation fleet, expanding our ability to observe and understand our home planet. So what is PACE bringing to the fleet? So first of all, PACE stands for the Plankton Aerosol Cloud Ocean Ecosystem mission. PACE was launched February 4th, just of last year, and our first data release was just 1 year and 4 days ago. There are 3 instruments aboard PACE. There's a hyperspectral scanning radiometer called OCI, and 2 multi-angular polarimeters, HARP2 and SPEX1. We'll go over them in detail on the next slide. The PACE satellite has global coverage. It has a 1300 local equatorial crossover time. It is a 3-year mission with 10 years of propellant that we hope to use up as well. The data products are free and open to all, as are all NASA Earth observation products. As for science goals, PACE is NASA's next great investment to advance and extend ocean biological, ecological, and biogeochemical data records, as well as cloud, aerosol, and terrestrial data records. So let's go over the instruments on the observatory. The first and the only one required by the mission is the Ocean Color Instrument, or OCI. It was built here at NASA Goddard Space Flight Center. It is a hyperspectral scanning radiometer that covers the UV through the visible through the near infrared. So that's at 340 nanometers to 890 nanometers. And it's at a 5 nanometer bandwidth with 2.5 nanometer steps, for those of you that like the details. PACE OCI also has 7 shortwave infrared bands as well. The temporal coverage of OCI is 1 to 2 day global coverage. Spatial is up to 1.2 kilometers squared at nadir. We also have 2 polarimeters on board. The first one here, the Hyperangular Rainbow Polarimeter, or HARP2. This was contributed by the University of Maryland, Baltimore County. It is a wide swath and hyperangular polarimeter. It has 4 bands, 2-day global coverage, 3 kilometer resolution. We also have the Spectropolarimeter for Planetary Exploration, or SPEX1. This one was contributed by SRON Airbus, some partners of ours in the Netherlands. It is a narrow swath and hyperspectral polarimeter with 5 viewing angles, and because of its narrow swath, it takes about 30 days for it to cover the whole globe, and its resolution is 2.5 kilometers at nadir. So for each of these instruments, they're each pretty great in their own right with some kind of novel or unique capability, and altogether they represent the most advanced global ocean color and aerosol mission to date. So altogether, PACE's products span the aquatic, the atmospheric, and the terrestrial domains. I've got here a few lists that are just kind of examples of different products we have. There's quite a few. If you're interested in knowing the full breadth of all the products available from PACE, please go take a look at our data product table webpage. This is a live and up-to-date list of all the currently available and future PACE data products. So please go check that out. It gives you descriptions. It'll link you to the algorithm theoretical basis documents and all the details you could want. And as for the rest of today, we're going to zoom in on this part. We're going to zoom in on terrestrial observations, specifically those from OCI. And I'm going to start here before I dive right into the products with basically the punchline about why we are here. Why is this meeting happening? So PACE OCI uniquely collects global repeated spectral observations. This is providing us with new views of changes over time of global terrestrial vegetation and the land surface. Also, these observations are a bonus of our mission, so rather than a mission-required product. We'll talk more about that in a bit. But the takeaway is they're less supported and they're also not as well known. So we want to get the word out to the terrestrial remote sensing community that these exist because we think there's a lot of potential. In fact, I think that we have started seeing the tip of the iceberg of capabilities for PACE land data. We're going to share this view with you today, particularly through Fred's presentation up next. We wanted to get the word out to you guys and get the data in your hands as an informed user. So this is what gave us the idea to start this group. And you as a community can help reveal the breadth of the PACE discoveries that we think lie below the tip of this iceberg that we're now seeing. Let's go over the provisional terrestrial products that are available from PACE OCI. We basically kind of have two types of products available. One of them are our new products that are hyperspectral enabled, so these are only really from PACE. For example, we have surface reflectance with 122 bands of surface reflectance. We also have 6 new vegetation indexes. Fred is going to go over each of these in detail, including how they're calculated, as well as some neat insights he's getting from them in the next presentation. We also have 4 legacy terrestrial indexes: the normalized difference vegetation index, or the NDVI, as well as the normalized water, infrared, and snow indexes. These are ones you all are probably more familiar with hearing about. And I also want to say, if you happen to have any suggestions for this list, if there's any products that are really broadly used, have been used for some time, and you think could be added, let us know through the survey at the end of this talk. So PACE is building on instruments that have flown for decades by NASA and other agencies, including one of the possibly best known ones, MODIS, which is on the Terra and Aqua satellites. So how do MODIS and OCI compare? Up here on the top row of this figure, we have spectral response functions of a subset of MODIS's 36 bands. And these bands go from the blue wavelengths around 0.4 microns to the thermal infrared at 15 microns. OCI, in comparison, has continuous spectral coverage from about 340 nanometers or 0.34 microns to about 0.9. PACE also has 7 shortwave infrared bands. And there's really kind of 3 places to call your attention to here. So for one, we can see here that PACE covers the UV, whereas MODIS does not. Right here, kind of in the solar reflective capabilities of MODIS and PACE are very comparable. PACE can basically do what MODIS can in that realm. And then out here on the edges, we do not have the spectral region to detect terrestrial solar thermal emission. So we don't have temperature, but MODIS does. As for comparing spatial resolution, MODIS is 1 kilometer, OCI is 1.2. As for temporal coverage globally, MODIS is 1 day, OCI is 1 to 2 day. If you would like to see reflectances of the two compared, again, I'm going to refer you to Fred's presentation. He's got a plot for that. And also, how does their data status compare? MODIS data products are and have for some time been standard NASA data products, whereas OCI data is still considered provisional. And what exactly does that mean? It's important to know your data status. So data status is a descriptor of the data maturity, where diagnostic is the least mature and standard is the most. All currently available PACE land data products have graduated to provisional status. So the results have been reviewed and are within expectations, but they have not been validated and may still contain significant errors. So make sure that when you work with your data, have this in mind. Of course, proceed with caution, because as provisional products, that means, like I said, they're being developed, they're not yet validated, and they are subject to change also in future data versions. So we may use a new atmospheric correction, we may add spectral bands or more products. It's just important to kind of stay up to date on what your data version is as well as your data status. And also notice that these are considered bonus products, as I mentioned earlier. These are bonus products provided by the mission, which from a NASA standpoint is very important to differentiate from a mission required product. That basically means to you practically as a user that with less mission funding and support, it might be slower for some of the data products to evolve. It also could mean that they're more malleable as well, that they're not set in stone, that perhaps this user group might help guide what the future versions of these products look like. And those of you who decide to be early users of PACE OCI data in your work, you all are going to be among the first cohort of users that will explore OCI's novel hyperspectral-based observations. And you will find informational and community support in joining the PACE Land Data Users Group, which is a great segue to an overview of our group. So the co-leads are myself, Fred Huemmrich, and Skye Caplan, coincidentally your speakers for today. The meeting frequency is quarterly. We're going to do this for at least a year, maybe longer. It's really going to depend on user need and user interest. So our group objectives are promoting greater awareness of PACE data, getting the word out there, building capacity and community around these products, and also soliciting user feedback. You guys are extra sets of eyes on this data. You can alert us to what's working, what could be better, and so on. And I want to emphasize this part here, that our content, the content of our meetings is always going to be user driven. We're going to ask what you all are interested in and build our meetings around that. And we are always open at any time to ideas and feedback on the group content and any events that we may have. So how do you join the PACE Land Data Users Group? The main way to consider yourself a member is to subscribe to our mailing list. This is what's going to unite us all in knowing when the meetings start, developing or knowing the date of the meetings, in getting the content of the meetings decided. You just send an email to join to the email shown here, PACE Land Community Request at lists.nasa.gov, and make sure you put subscribe in the subject. You don't need any text in the body of the email. Send it. You'll see an email to confirm your address. Just reply to that. You don't have to put anything in the email, just reply. And then once you see this welcome email, you have joined successfully. If you have any issues with it, you can send an email to the email at the bottom of the screen there. The second way we want you to be a part of the PACE Land Data Users Group is to attend our meetings and really participate. We want this to be interactive. And also we ask that you respond to any of the short kind of surveys that we'll send out each quarter that are going to help us develop the next meeting. So moving along to this, I am the PACE applications lead, as I mentioned earlier. Because of time, I didn't have time to go over our PACE applications program today, but I do want to give a shout out to the fact that we are seeking terrestrial applications partners. So what does that mean? So PACE applications works with individuals and groups across public, private, nonprofit, government, university, basically any sectors who are looking to integrate PACE data into decision-making, business, resource management, or any other of a spectrum of broad applications capabilities. So the question is, if you are doing applied work, does your applied project have direct economic, health, or other benefits to society? So this is in contrast to the way that like foundational research benefits society, broadly. In this way, do you have ones that maybe, for instance, might influence public health around air quality or water quality, topics like that. And partnerships with us, if you become a PACE applications partner, these partnerships are designed to specifically amplify the applied research and development efforts that you're doing and accelerate the translation of PACE observations into action. So these are unfunded partnerships. They are application based. So if you go to this website here, you can find the applications. I also encourage you, if this sounds at all interesting, to please go to this website here, read the details of the program, go through and look at a few of the partner profiles to kind of get an idea of what people do, and then consider applying. The application is on that page. We'd love for you to consider to join, and we review the applications approximately quarterly, every couple of months. So with that, I want to say thank you so much for joining us today. I want to remind you, don't forget to subscribe to our mailing list if you would like to join the group. Remember, there is an event archive. The content will be available in a week, hopefully less. You can have a recording as well as a transcript of all the question and answers during the session, and also all of our slides. Finally, I want to say, please definitely fill out this survey today. Your feedback very much helps us with the goals of this group. Thank you very much for listening today. Next up, we have Dr. Fred Huemmrich. He is a research professor at the University of Maryland, Baltimore County. He is a member of the PACE Science and Applications team. And broadly, his research focuses on using remote sensing to describe biophysical characteristics of terrestrial ecosystems and utilizing that information to improve understanding and modeling of ecosystem processes. He has performed fieldwork in a variety of different ecosystems, doing work at on NASA field studies in grasslands, boreal forests, and Arctic tundra. He's going to be giving a talk today on PACE terrestrial products, a new view of ecosystem traits, land cover, and productivity. Take it away, Fred.
Hello, I'm Fred Huemmrich, and today I'm going to talk about PACE land products and provide some examples of using PACE land products to study terrestrial ecosystems. Although PACE was developed as an ocean and atmosphere mission, it can provide useful data over land, and I'm going to try to demonstrate that in this presentation. There's some real advantages to using PACE data. It provides repeated spectral imagery over the entire planet, and therefore is useful for developing time series of spectral information, and from that, because it provides spectral reflectance, we can develop algorithms and test them in ways that we really haven't been able to do with previous satellite systems. In addition, although PACE's pixel size is quite large, It can complement existing sensors with higher spatial resolution characteristics, such as emit, nmap, prisma, and desis, by providing improved temporal coverage for the more infrequent higher spatial resolution observations. The PACE ocean color instrument terrestrial products come in two levels, level 2 and level 3. On the left shows level 2 data, which is swath data, which has not been projected, is the native spatial resolution. That's 1.2 kilometers at nadir, but PACE doesn't really view it nadir. It always tilts at 20 degrees because it's an ocean mission to avoid glint. And it also has a fairly wide swath of greater than plus or minus 50 degrees to get the global coverage. The level 2 swath data comes in 5-minute granules, and the figure there shows one 5-minute granule projected onto the Earth to give you a sense of the scale of that. The level 3 data are globally mapped in latitude-longitude grids, and they're gridded at two spatial resolutions, one at 0.1 degree, which is approximately 11 kilometers at the equator, and the other at 2.5 minutes, which is about 4 kilometers at the equator. The level 3 data are averaged at daily, 8-day, and monthly time periods. This figure shows the terrestrial surface product where the spectral bands are in it. This version 3 surface reflectance product provides 122 spectral bands, and here the red lines and bars are showing the locations of the spectral bands projected onto reflectance spectra for some typical green vegetation to show where the bands lie on a reflectance spectra. From the ultraviolet to the near infrared, the bands are 5 nanometers and spaced at 5 nanometer intervals, except for a couple of places where you can see gaps. These are there due to problems with the detectors, or the atmospheric correction produces bad data, so those aren't provided. You can also see some areas where the bands seem to be redder, more closely packed. In those regions, it's still 5 nanometer bands, but it's oversampled at 2.5 nanometers in those spectral regions. And then in the shortwave infrared, you see 5 spectral bands. These are very close to being the MODIS SWIR bands. The surface reflectances are calculated using an algorithm called L2Gen, and these agree fairly well with the MODIS surface reflectances in these comparisons here. L2Gen calculates the surface reflectance based on atmospheric absorption and atmospheric scattering. It does not include aerosols. We plan for future versions of the surface reflectance to use a more advanced atmospheric correction algorithm called ISOFIT, and but that's again in the future. What we get then from the spectral reflectance, PACE spectral reflectance data is time series of spectral reflectance, and these are two examples of 8-day average spectral reflectances over time at two different sites. There are two sites I'm doing field research in, and one is a tall grass prairie in Kansas, the other is a boreal forest, and you can see how we can the data provide examples of, in the case of tall grass prairie, we can see it going from early in the season when there's no green vegetation to greening up and then going back into senescence into the fall. In the boreal forest, you can see the early springtime snow cover thawing out, melting, and then the system greening up. This is what's really exciting to me about PACE, because up until now, it's been very difficult to get these kinds of time series of spectral reflectance data. It's expensive and logistically difficult to have aircraft flights repeatedly over the same place, and it is time consuming and hard to just even go out there with a a spectrometer on the ground and make these kinds of measurements. So we don't really have much data where we see these kinds of time series. And now with PACE, we have it everywhere on Earth. In addition to the spectroreflectance, PACE also provides a vegetation index product. 10 vegetation indices are calculated in the LandVI product. These include NDVI and EVI, which are the traditional greenness indices related to green leaf area, and are available. And these are continuations of these indices that are available from MODIS. NDWI and NDII are make use of the near IR and SWIR bands to detect water content and amount of foliar water. The chlorophyll carotenoid index, CCI, provides information on photosynthetic efficiency related to leaf pigments of chlorophyll and carotenoid ratios. And then the normalized difference snow index describes the presence of snow and the fraction of snow cover within a pixel. But we also provide from PACE are new indices, that is, new to NASA satellites. These are generally related to the amount of foliar pigments, and we're able to calculate these indices because of PACE's narrow hyperspectral bands make these possible. And so they're referred to as hyperspectral enabled vegetation indices. So they're related to pigment context. There's the chlorophyll red edge index that describes canopy chlorophyll content, a carotenoid index that describes canopy carotenoid contents. The carotenoids are yellow pigments. When you see leaves turn in the fall, the yellow leaves, that's the carotenoids. You're seeing the carotenoids there, and carotenoids are used in leaves for photoprotection and also can provide some ability to enhance photosynthesis by absorbing energy in spectral regions that chlorophyll doesn't. Then the anthocyanin reflectance index gives a description of anthocyanin content. Anthocyanins are red pigments in leaves. Again, in the fall, when you see the leaves turn red, that's the anthocyanins you're seeing, and those pigments provide photoprotection for the leaves and also provide an early indication of senescence. And then finally, the PRI, the photochemical reflectance index, which describe status of xanthophyll cyclepigments. Xanthophyll pigments are a type of carotenoid pigment, and these are used by plants for photoprotection and have been shown to be related to photosynthetic light use efficiency. So we can use these indices and look at them over time to see the dynamics of vegetation, the phenology of vegetation. Traditionally, phenology studies, satellite-based phenology studies, have used NDVI to look at the change in vegetation, green vegetation amount, and looking at things like the timing of green up and the timing of green up and the timing of senescence. In this time series plot for tall grass prairie, the blue line here is the NDVI, so the traditional phenology plot, and you can see the timing of green up and the timing of senescence. This green line, pale green line, is the chlorophyll index, which is more closely related to vegetation productivity than NDVI is. And you can see how the timing of green up and the timing of senescence are different between these two different indices. The third thing we can see on this plot is this dark green line, which is the ratio of the carotenoid index to the chlorophyll index. Now, these indices, like the carotenoid index, is related to the overall canopy carotenoid content, which is the content per leaf times the leaf area. By taking the ratio of these indices, what we're doing is mostly canceling out the leaf area effect and highlighting the within leaf pigment ratios. And we see how in the spring we start out with relatively high carotenoid content and low chlorophyll content, and as we move through the spring into summer, the amount of chlorophyll increases and the ratio drops, and then as we move into the fall and senescence, then we see the amount of chlorophyll again dropping off and the amount of carotenoids, relative amount of carotenoids, increasing, and that ratio can be related to photosynthetic efficiency. Here's an example for that boreal forest site in Alaska, and we see here that once again we see the blue NDVI. There's a couple of gaps here due to some clouds. See the blue NDVI, and then we see the green of the chlorophyll index, and we see how the chlorophyll index, once again, the timing of green up and the timing of senescence when looked at from the chlorophyll index is very different than the timing from the NDVI. But we also see here, in terms of the carotenoid to chlorophyll ratio, is these big spikes in the spring and in the fall. And what's happening here is for these evergreen spruce trees at this site, what we're seeing is the changes in the foliar pools of chlorophyll and carotenoids, and which is related to the onset of photosynthesis at the start of the season and the shutting down of photosynthesis and the hardening for winter at the end of the season. And so this is really telling us something that we hadn't been able to see before about the timing of the start and end of the photosynthetic season for these boreal forests. And we can carry this on to the entire planet. And so these images are RGB images where green is the chlorophyll index, red is the anthocyanin index, and blue is the carotenoid index. And so the colors that you see here are basically representative of the relative amount of these three pigments in the leaves. And so you can see how that's changed seasonally. And in general, the brightness of a pixel in this is related to the LAI, and the color that is related to the relative amounts of the pigments. If we look at Eastern North America here, as we start through in the spring, you'll see here in the spring that it starts out on this map, it looks blue, which is showing us the early leaf emergence where the leaves are relatively high in carotenoids and low in chlorophyll. And then as we move into summer, we see that the area greens up, that the chlorophyll comes into the leaves and takes and becomes the dominant pigment of the leaves as they move into summer for full photosynthesis. And then as we move into the fall, you see that the colors start to change to blue and red as the chlorophyll was removed from these deciduous leaves, and we see the fall colors. And so we're seeing this in the PACE data, and this is the first time we've ever been able to really look at these kind of global patterns of leaf chemistry. In addition to looking at plant pigments and traits, we can also use PACE to do land cover classifications. Here's an example of an area of northern Alaska and northwest Canada, which is part of the above NASA experiment that I'm working on. And in this case, I've used summertime PACE data and did an unsupervised classification to show different regions. And if you look at the spectral characteristics of the classes, one of the things I find interesting is it breaks down really into sort of, we see multiple classes, but the classes themselves break down into two types. There are the ones with these lower visible reflectances, and these really appear to be dominated by vascular plants such as graminoids and shrubs, and we're basically seeing variations in leaf area here. And then there's a second set that have higher visible reflectance, and the shape of these spectral reflectances look more like lichens. And so these are probably sites that are more lichen dominated with varying amounts and types of lichens in them. So this is the kind of classification and interpretation of classes that we can get out of PACE data. We can also use PACE data to look at ecosystem productivity, ecosystem function. In this case, I have looked at uh, gross primary productivity measured by flux towers as part of the NEON study. I've looked at 44 different flux towers here, which represent vegetation types from tropical forests through Arctic tundra. The goal of NEON is to monitor ecosystems within the United States, and they have tried to put flux towers in every major vegetation type in the United States. So this is what we're capturing here. I've averaged the gross primary productivity from the towers to 8-day averages that I'm matching up with the 8-day average PACE data for the extracted for those sites as well. And this is for data covering periods from March through September. So we're getting most of the growing season. So we're looking at a variety of vegetation types throughout the growing season in a variety of sites. And when we use a partial least squares regression here, and these are showing the coefficients from that, we're able to describe over 80%, describe 80% of the variance in that GPP data with a root mean square error of about 4. And you can see, this is a range of about 0 to 30 to give you a sense of the errors here. And then also from the partially squares coefficients, we can see the coefficients and see different spectral regions that are important in retrieving these, including the red edge, blue, and SWIR bands. But we can actually focus in at specific sites. This is data for the Guanica tropical forest site, dry tropical forest site in Puerto Rico. And again, a time series here, and this is showing the orange line is showing the GPP calculated from the flux tower there. And we see this pattern of starting low, going to a peak, going down to another low, going up to another peak, going down to another low, going up again. The blue line here is a calculation of gross primary productivity based on a partially squares regression focused on this type of vegetation. And we can see that it does a really good job of tracking this pattern of increasing and decreasing productivity in comparison to the green line, which is NDVI. And we can see how NDVI really does not change at all through this drop and increase. And again, here and later in the season, it also is not changing at all in response to this. So PACE spectral data is able to provide information on the dynamics of this ecosystem that we just really can't see with NDVI. So just to wrap this up, I hope this has shown you something about the ways in which PACE data can be used and suggest to you some of the possible applications of it. There's a lot more that can be done with PACE data. This is just very much scratching the surface, but I hope that this encourages you to look at PACE data and try to work with it yourself. And thank you for your interest. And also, I want to thank the NEON for providing the data and my support for working with the PACE data. Thank you.
Next up, we will hear from Skye Caplan. She is a scientific analyst on our PACE team. She has a diverse background with a bachelor's degree in geology and astronomy and a master's in remote sensing and biological science. She is currently our phenomenal land lead for the PACE mission, meaning she's the one working behind the scenes here at NASA Goddard to make these great land products a reality. So she's presenting on PACE Terrestrial Data Access and will give us all an overview of how to download these terrestrial data products. Take it away, Skye.
Thank you, Fred and Morgaine, for those amazing presentations. Now that we know a little bit about PACE data and how we can kind of start to use it, we can get briefly into how to access all that good data that Fred and Morgaine just finished telling us about. This presentation isn't meant to be super in-depth, but instead is just supposed to show you specifically, in the simplest way, how to access PACE terrestrial data. Before we get started there, I just want to mention a couple really useful resources for accessing PACE data. First is our data access landing page. We update it as frequently as possible with new resources, like release notes and data access options, so be sure to check back for new information periodically. Another great resource is the Help Hub, which you can find on the Ocean Color website, but the stuff in there is super useful for land data processing as well. The Help Hub has tutorials written mostly in Jupyter Notebooks on accessing and analyzing PACE data. So for those of you who prefer grabbing data through Python rather than through GUIs, there's a really succinct tutorial on using the Earth Access package, Python package, to both download data locally and to stream it in the cloud. And if you don't quite know what that means, then you should also head over onto that link to learn more about it. So let's actually get into it. To begin, here's some terms we use quite often when talking about the data that some of you might not be familiar with, so I'll go over it to get us all on the same page. These slides say a little more than I'm going to say in words, but I'll just go over the basics. So first is near real-time, or NRT data, which is the data that comes from the satellite and is processed as soon as the system can get to it. This is in contrast to refined data, which is data that is reprocessed with the best available ancillary information. And these files, rather the refined files, are typically available about 1 to 2 months after the corresponding NRT data is released, just due to the availability of that ancillary information. Next, we have data processing levels. So when I say level 2 data, what I'm talking about are those regional 5-minute granules that haven't been binned or projected yet. These data are at the native OCI resolution, so that's about 1.2 kilometers at nadir. The level 3 data, by contrast, are global data. That means like data over the whole globe that have been binned and reprojected. So there are L3B and L3M files, so level 3 binned and level 3 mapped files. And if you're looking for the actual data in the suite, you're going to want the L3M or L3 mapped files, not the L3Bs. Hopefully we're all on the same page now with terminology. And with that being said, the easiest way to get PACE data outside of Python is to do it through Earth Data Search and their GUI system, which you can find at, if you Google Earth Data Search, I'm not sure if that link is going to be clickable here, but basically, yeah, Google Earth Data Search and you'll find it. Whenever I'm looking for one of the PACE products, I go up into that search bar there in the top left and type in OCI and the name of whatever product suite I'm looking for. So if it's surface reflectances, you'll type in SFREFL, or if you're looking for the vegetation indices, you'll type in LandVI or LANDVI. When you hit enter, you'll bring up the matching collections, and whether you need level 2 or level 3 data, the one thing that I want everyone on this call to remember, other than Fred and Morgaine's fantastic talks, are to check your version. Please always use the most updated version of any dataset, and ours especially in this case. So right now, PACE data is on version 3, at least for PACE OCI. Also, unless the data you're looking for is super, super recent, within that 1 to 2 month time span, you'll want to use the refined data collection that I mentioned before, so the one without near real time in the designation. So in the example on the screen, you'd want the second red box there, not the one at the top. If I were to click on that second red box, I'd get this screen. The collection initially won't do any filtering data for you, so instead you'll want to go to that sidebar there and input some search parameters to narrow down your options. One of the most useful things, in my opinion, is the granule ID search option, where you can use asterisks in combination with unique identifiers of the type of data you're looking for to get really specific. So in this example, say I'm looking for 8-day average PACE data at 4-kilometer resolution, I'd plug in asterisk 8D, asterisk 4km, asterisk .nc into the search bar, and it would bring up only files with 8-day and 4-kilometer designations in the file name for me. Of course, you can also filter by day as you would with any other application. In addition to filtering data, a really amazing feature of the Earth Data Search tool that I just figured out about recently and I love already is the subsetting functionality, which I think a bunch of you in the audience will find really, really useful, especially those of you working on case studies. Basically, you can draw a polygon or upload a shapefile of your area of interest, choose some files to download, and Earth Data will automatically deliver those files subset to that polygon that you provided. Since PACE data, and especially the surface reflectances, can get pretty big depending on which files you're downloading and how many you're downloading, this is a really great way to reduce the amount of data you're downloading and reduce your data processing needs for your project as well. So in addition to the filtering I showed you on that side, what you'd want to do is click the icon that looks kind of like the crop icon on your phone and either draw or upload your polygon. Then after you're finished selecting your desired granules with the little plus boxes on each on the bottom of each section there, you'd go ahead and click download to take you to the next screen. This is what you'll see when you do that. In order to apply that spatial subset, make sure you select Customize with Harmony in the first section there, as well as a subsetter in that service dropdown in the second section. That way, your data will automatically be subset to your supplied polygon. I also want to quickly mention one more option you'll have, which is to subset the variables included in the file. So say you're only interested in the hyperspectral enabled vegetation indices from PACE and you'd rather not have to deal with everything else that would automatically come in the file. Before you download your data, you can select that Edit Variables option and select the specific data that you want included in your file. I, of course, would advocate that everybody at least choose to include the navigation data for your latitudes and longitudes, and the sensor band parameters group can be pretty useful as well. Basically, maybe download a full file first to get familiar with the data and what's in the files before removing anything. Then you can click download and get your file subsets. I just think this is a super valuable tool, especially for those of you working in specific areas who might not otherwise want full granules. If you're just looking for a quick way to browse level 3 global data, you can also do that on the OBDAC level 3 browser, which a link will be provided to you in the Q&A document posted on the events archive page. It's a quick and easy way to download individual data files. You just have to have the right filtering terms to find them. So like Morgaine and Fred both mentioned, these products are at provisional status, which is what you'd put into that first box at the bar at the top of the page. And then you'd click, you can filter based on the instrument, product, period, and resolution that you want. Then you could click the image that you are interested in downloading and click either SMI for that level 3 mapped file or the bin or capital BIN link for the level 3B files. And that's it. There's also longer, more in-depth Earth data search tutorials that aren't PACE specific, which you can find also by Googling Earth data search tutorial. But I hope that makes finding PACE data a little less daunting for you all. We're really excited to see what you do with this data and the interesting science questions you'll answer. So please do take some time to play around with it. So yeah, thanks for your attention. And if you have any questions about PACE, what you've seen in this presentation, in this call, I'll note that the Earth Data Forum is a great place to post any of those questions where your colleagues can see them, which I know is a little daunting, but if you have a question, I'm sure they do too, and it'd be great to kind of get those answers out to the community. Of course, you can also always reach out to me or the applications email as well. We can try to direct you as best as possible. Anyway, thank you.
One really important note before we finish up today. A lot of great questions were asked by the audience during the live meeting through our chat feature. So if you would like to see those great questions and our speakers' answers, please click the blue button here to access a transcript of all the questions and all the answers. Thank you very much for joining us for our presentation. We hope you enjoyed learning about PACE land data and our new users group. Please do fill out the survey that is linked here, even if you did not attend the live meeting, if you are attending or watching the recording later. We really appreciate the information from that survey. Again, thank you very much for joining us and have a great rest of your day.